Okay, everybody, we're going to take a look at the single arbitrary, and there's quite a bit of background material that you'll want to cover. Page 519 through 521 walk you through the model for what we call a single channel waiting line. And page 502 illustrates this, okay? And essentially what it is it says, okay, in this model, which is the MG1, we assume that we have one channel, for our arrivals and to service them. We have an arrival time that is it has a general probability distribution, and then the M denotes a Poisson probability. So we know that we have averages and standard deviations, so it fits a Gaussian model, but it also fits a Poisson model because Poisson distributions come in clusters. Like people come to a lunch, there's a lunch hour at rush, there's a dinner rush in a restaurant or an ATM, people come in after work or they come in at noon, that type of thing. So that's what we're dealing with. We're also dealing with the issue though, over in figure 11.4 of the general shape of the waiting lines cost, okay? Total cost, and bouncing off that with service costs and waiting costs. And notice as service cost goes up, waiting cost goes down. If you want to see it illustrated, you can see that structure of a waiting line system or a single waiting line. They show you that in figure 11.1 at the bottom of page 502. And then they begin to walk you through the mathematics of it over in page 503 and page 504 there. And in table 11.1, they show you probabilities, Poisson probabilities for the number of customer arrivals and this is a Burger Dome restaurant. And they show you how those probabilities are computed, okay? And the mean number of units, that can be called, that can be served the service rate. So those are there, and you can take a look at those. Now, today I'm gonna share my screen, okay? My desktop, and I'll open that up. This is the file from the single arbitrary file for chapter 11. And what we're to do today is to use goal-seek to obtain the service cost per channel, and we're to assume the waiting cost per unit is $1.16, and we want to have a total cost per period of $2.99. So we're trying to figure out what is our service cost, okay? And if you look at figure 11.4, page 518, you're going to see we're trying to figure out total cost. Let's scroll this down here for a minute. Total cost per time period. And we have two things that figure into that, the waiting cost per unit and the service cost per channel, okay? And again, I can't emphasize enough to you that you really do need to just walk through the steps over on page 520, especially so that they show you the computation for the probabilities that there are no units in the system, then the average number of units in waiting line, average number of units in the system, average time a unit spends in the waiting line, average time a unit spends in the system. Because remember, there's waiting time and then there's service time. So that's the total amount of time. And then the probability that a unit has to wait for service. Now the logic of that, and the math of it's worked out over on page 521, okay? And if you look here at rows 14 through 19, this is the single arbitrary file out of chapter 11 in the text files, the data files. You'll see that those mathematics worked out. I want to show you something. If you take a look at row 14, you're going to see the probability that no customers are in the system, okay? And that's going to be 1 minus B7 over B8. And that's going to be 1 over the arrival time divided by the service rate, okay? And think about this for a minute. Now, to get the probability, probability is always equal 1, okay? So if we want to compute the probability that no customers are in the system, then we know that there's going to be some customers in the system, and we'll figure the probability of it. But right now we're going to look at the probability that there are none in the system, and we take that and by dividing B7, the arrival rate, by the service rate. And and it makes a lot of sense. The arrival rate, okay, the probability that people will come, that percentage, and then service rate tells us how many people are basically in the system at any given time. So we get B7 divided by B8, okay, and that's 0.35 divided by a service rate of 0.5, and we get this figure, which is 0.30. This is B7, the arrival rate, 0.35 divided by 0.5, the service rate. How fast do they come in the door? How fast do we take care of them? Okay. Now, if you look down here at row row 19, you're going to see that the probability an arriving customer has to wait is 70%. So let's think about that for a minute. The probability that there's no one in the system is 30%. Okay. If that's true, then the opposite of that is someone who comes in and they have to wait would be 0.70. That only makes sense that the two of them add up to a 1 in terms of the probability. Then we get the average number of customers in the waiting line. Okay. The average number of customers in the system. The average time a customer spends in the waiting line, and the amount of time a customer spends in the system. Remember, the system is comprised of 2 time periods. Okay, the time that the person or the unit is waiting, the amount, and then the time that the person is being served or being taken care of, or the unit is being serviced, or whatever we're working with. In this case, we're doing arrival times. Okay, and that just makes sense. So the probability that they're waiting, or the probability that they are being served, together is going to equal 1. Then we have to couple that in with the arrival rate. Okay, and that's where the Poisson comes in, and we use that. Now, we'll look at each of these averages, and here it is. And again, these are right from page 521, and you'll see those numbers where they show you the formula. Okay. And we see the standard deviation over the mu. And then we see the arrival rate over the service rate. That's where we get that 0.35 by 0.50. Then we see the arrival rate squared. Okay, and then that's times the standard deviation of the service time. And then that's plus that arrival rate divided by the service time over 2 times 1 minus that probability. So you can see how those numbers all plug themselves in. And that's basically rows 14 through 19 there in the file. And you could just simply take the symbols and plug in the numbers, and away you go. Well, that's the complicated part. The nice thing is we have models that we can plug these data in, and the probabilities, we can simply plug these in if we know the arrival rates, the service rates, and the standard deviation of the service time. Okay? And then it just becomes a matter of plugging them into the model. And this is this file is a pretty typical model. Now we have the average number of time in the waiting line, number of customers in the system, time they spend in the waiting line, time they spend in the system, and there's a probability that an arriving customer has to wait. Now we're ready to use goal seek, okay? So we're going to click on data, then we'll do what if analysis. We'll click on goal seek, and we want to determine the service cost per channel, okay? And we're going to assume the waiting cost per unit is $1.16, and we want to obtain a total cost per period of $2.99. Let's assume right here, just we'll click this off for a second. Let's assume that the service cost per channel is right now is 99 cents. Okay. Now let's click on our goal seek. Okay. And we want to set the service cost per channel. We're going to assume the waiting line is waiting cost per unit is $1.16. Okay, we've got that. And so we want to set the total cost per period to $2.99. So we'll click on cell C27. And then we want that to be 2.99 by changing the cell here, B25, and we'll run the goal seek. Now here's something very interesting. We changed the service cost per channel by 10 cents. We lowered it, and we lowered the total cost per time period by 10 cents. But to put that number in perspective, take a look for a moment over there at page 518. Okay, we have a total cost per time period. Okay, and here in that example they have it per hour. But it could be by the time period. We have a service cost per channel. Okay, and we're assuming the waiting cost is there at 116, and so we reduce the service cost. Okay. And notice, as we reduce the service cost, we're going to end up having the intersection of the two of them, service and the waiting cost, the intersection point is going to be driven down. So the total cost, time cost per period, will itself come down, and we get an intersection there of service cost and waiting cost. So you'd say, okay, what's the practical takeaway from this? Well, again, remember the model that we're working with. We've got a single channel model, okay, waiting line model. We have a Poisson arrivals, and we have arbitrary service times, okay? And that means, for example, in the ATM, and they're in the textbook, they give us that model. And over on page 5, bottom of page 520, they talk about retail sales at the seafood supply. Okay, and they give us the handled by one clerk. Customer arrivals are random. The arrival rate's 20 customers per hour. Okay. And they had done a study of their service processes. So and they got the service time. This is all the verbiage there at the bottom. And they're trying to figure out, do they want to hire a second clerk, okay, or not? Well, you could see if I get the service cost per channel down, I can reduce the total time cost per period. Okay. And basically, okay, if we add a second clerk, okay, then we're going to be talking about reducing the waiting cost per unit. Now let's look at this for just a minute. Now we ran the goal seek, okay, and we reduced the service cost per unit, okay. So I'm going to do the goal seek. Set this cell to 2.99 by changing the cell, service cost per unit. OK. And the service cost per unit then drops to $2.99. Service cost per channel. Okay. Now, if we can assume that we can get the total cost per time period down, it would be worth our while to go ahead and add that second clerk. But let's look at it. And I'm going to depart from the text a little bit and think about some of just the practicalities of this. The waiting cost there, okay, and let's see what it does. Let's take it down 10 cents to 106 and see what happens. Because we can kind of simulate a goal seek here. Now, we reduced the waiting cost per unit by 10 cents, okay? The total cost per time period was 8 cents. So here's the bang I got for my buck. I spent 10 cents, okay, to reduce the waiting cost, because I'm going to assume that the service cost is arbitrary. And so I spent 0.10, 10 cents to reduce the waiting cost per unit, and I got an 8-cent reduction. So I'm going to see what kind of rate I've got here of return. Now I've got about an 80% return. In other words, I don't have a straight one-for-one. The marginal utility on this is not just a strict one-for-one. For every penny I reduce, okay, the waiting cost, I reduce the overall total cost by 0.8 of a cent. Okay, so that would give me a way to take a look at it and figure out am I getting the kind of marginal utility out of an additional server that I want. Okay, folks, that's it for this case, and I appreciate your time. And of course, I'll make the key available, and well as this recording available after it's due. Have a good one, and we'll stop the share. So I'll go back to this meeting. And we'll stop the recording, and you have a good one.